Hi,
Hi,
Abby.
sir.
How are you doing?
I'm good. How are you?
Good, good.
That works for me. Okay.
That's okay. That's okay. Perfectly fine. And now, beginning with our class on calculus. Amy, how do you find so far? How's it going? And what have you learned so far in short?
Well, I've learned so much. Just overall, I think the most important thing was getting like graphing. Um, I think now, before it was just sketching it, doing a rough sketch. I knew the end behavior and I knew like roughly where the graph was going. But in terms of turning points and things, and the maximum and minimum, I didn't actually know exactly what I was doing. Well, now I've definitely got um, like the actual values, which helps. But obviously, with more knowledge and things, I can do it a bit more faster and a bit more easily because still I'm referring back to things, but that just comes with practice. And just generally about tangents, gradients, derivatives, finding derivative of any function. That's quite cool. So I can do that. And yeah, hope
That's
I can do more things to come.
perfect. So, as you correctly said, we're working with polynomials and other functions earlier. And in functions, we could always sketch the functions, knowing their zeros, multiplicity of zeros, and behavior, symmetry, and so many other things. However, we were unable to find the exact point for maximum and minimum, rather the turning points of on the graph of a function. Now, with calculus, we can actually calculate these turning points, and we know exactly where these turning points are. More than that, we also understand better about the shape of the graph. Where is it concave up? Where is it concave down? Right? And in between, where the concavity changes, those points are called point of inflection. So in today's lecture, we'll more focus on increasing, decreasing behavior, concavity, and the point of inflection. So once you understand how these things get connected, then you can actually give a proper shape to your graph, not just joining the points which you know, but how the graph will be joining those points to really represent it is what we are going to learn today. I'll also introduce to you the concept of a second derivative and higher derivatives as we move along. Okay,
Okay.
let me share the screen with you. Here is the lecture. We'll actually talk about higher derivatives, and that is the title given to you. Now, we'll begin with simple concepts which you already know about increasing and decreasing of a function. We see a function is increasing when its value is increasing. For example, this function graph given in green, this is the increasing interval for the function. And this is also increasing interval of the function. Correct? But
Mm-hmm.
when we say increasing, decreasing function, at that time we are specifically saying that in the entire domain of the function it is increasing or it is decreasing. Okay? Which will be the case for which function? What do you think? Which function will increase in the entire domain?
Um, Cubic.
Perfect. So cubic function will increases in the entire domain, right? Similarly, decreasing function will be a reciprocal function, 1 over x, which in its entire domain decreases.
Mm.
However, most of the time, functions will be increasing in some interval and decreasing in the other. For example, a parabola itself, y equals to x squared, it decreases first until the vertex, right? And then increases after the vertex. So it is combination of both decreasing and increasing. So the functions may have turning points. As you can see here, the graph in red, it is decreasing, and at turning point it turns increasing, then again it turns decreasing, and then again it increases. So most of the time functions will have this characteristics of increasing and decreasing behavior. Apart from this, if you look at these two graphs on the screen, you find some critical points. To sketch these graphs from the equation, what we need to really understand are these points where they turn, correct? Or the points where they have the x-intercepts. And also important is this portion, which we define as the concavity. What I'm trying to say here is that this portion of the graph is concave up, right? Do you see that?
Yeah.
Concave up. But on the other side, this portion of the graph is concave down. The point in between is called point of inflection. Today, we'll focus more on this point of inflection and how to find the concavity of the graph. Where does it change with the help of higher derivatives, right? So let me begin with talking about the concavity itself. So let's take a very simple example. Parabola is one of the easiest graphs to sketch. So I've taken an example where the function is x squared minus 4. That means a parabola has been translated 4 units down. Correct? Now you can see that this parabola opens up. So whenever parabola opens up, that shape is called concave up. Is that clear?
Yeah.
When we say concave up, that is the shape which this parabola opens up gives you. That is concave up. Now, if I try to draw tangents at any point on this parabola, so I've drawn 3 tangents, and these are the 3 tangents I've drawn on the parabola. Correct? So what do you notice about them? All the 3 tangents are below the graph. Do you notice?
Yeah.
Above the tangent. So when it is concave up, then in that case, you notice that the tangent at any point is below the graph. Correct? Now,
Is it just for this graph?
any concave up graph,
But what
any
happened if it was? What happened if the turning point was at 0, 0?
yeah, zero anywhere. So see, when it was concave up, tangent is below. Do you see that? Let's take the picture which we began with. Okay, now here the concave up portion, if you draw a tangent here, tangent is below the graph. Do you see that? Let me clean this up. Let's talk about the red graph. So the function, which is quartic function, if I draw a tangent here, do you see the tangent line is below the graph?
Yeah.
So if you draw a tangent on any part of the graph which is concave up, let's say this portion is concave up, right?
Okay.
Then the tangent is below the graph. Do you see that?
Mm.
So if the graph is concave up, the tangent is below the graph.
Oh, okay.
That's what I'm trying to say, right? So position
Yeah.
of tangent and position of graph makes it very clear. On the other hand, if you have a graph which is concave down, which is like this, do you see that? If I draw a
Yeah.
tangent, it is above the graph.
Oh, okay. Yeah.
That's what I meant. You get the
That
idea?
makes sense. Yeah.
Correct. So we're just trying to see few characteristics which we could, make use of while understanding the curves better. Is it okay?
Mm. I thought you said, sorry, below and above the x-axis. That's why I was getting so
No,
confused.
graph.
The graph. Yeah.
Okay. Right. Now, gradient, as you know, is changing as we move from left to right. The tangent here has a negative slope, right?
Yeah.
0 and positive. That means gradient is increasing. You see that?
Yeah.
So we can say gradient changes from high negative value to 0 to high positive value, right?
Hmm.
As we move from left to right. So it always increases. So if you have a concave up graph, in that case, gradient, which means the derivative, is always increasing as we move from left to right.
Oh, yeah.
Correct? So gradient is rate of change, right? So we can say rate of change is positive. So now, if you see a graph which is concave up, we can say a few things about it. One of them, if you draw any tangent at any point, tangent will be under the curve. Second, any point when we move from left to right on the graph, the gradient is always increasing and positive. Is that clear?
Yeah.
Increasing, I should say increasing. Right? So when we say gradient is increasing, right? So that means, and for this particular graph, f of x is x squared. What is the gradient? 2x, correct?
Yeah.
So you can see the gradient. 2x means 2 is the slope, right? For a straight line. So
Yeah.
this particular graph in red is the graph of the gradient, which is increasing. Does it make sense?
Yeah. Yeah.
So you have your function f of x, which is in green, and you have your gradient, which is in red. And you can see it's a straight line with a slope of 2. 2 is positive. Perfect. Now, if I flip the situation and now take the parabola, which is opening downwards. So now the equation is f of x is minus x squared plus 4. So now the graph has concave down. It opens downward. This type of graph, which opens down, is called concave. And here, if I draw a tangent line, it is always above the graph.
Yeah.
And in this case, as you move from left to right, you see the gradient, the
It's
slope of the
always,
tangent line. It is positive, 0, and negative. That means gradient is decreasing, correct?
yeah.
It moves from positive to 0 to negative, right? So it is always decreasing as you move along the graph. Clear?
Yeah.
So, Amy, can you summarize for me what is the relation between concavity and tangents?
Right. So if we have concave up, any point
Tangent at
on,
any point.
oh right, okay, so at any point tangents will be below the graph,
Correct.
and if you so any point from left to right, it's always increasing, because on concave up we're going highly negative, 0, positive,
Perfect.
so always increasing. Concave down, at any point the tangents will be above the graph.
Yes.
And it goes from, so the tangents, so at any point it will go from positive to 0 to highly negative, so therefore it's always decreasing.
Perfect. Now here are 2 questions for you. Can you answer them for me, please?
Yeah, so how do you relate concavity with position of tangent on the curve?
You have already answered. Correct. Question
Yeah.
number 2.
What happens at a point where the concavity changes?
That's
So
good. Now it's about a thing. When we have a graph which is concave up, tangent is below, and when the graph is concave down, then the tangent is above. But what happens at a point where you may have a situation, as we had right in the very beginning of our example, the concavity is changing. So what happens to the tangent at a point where, say, for example, let me mark the point here, where the concavity is changing. What will happen to the tangent at this point? Will it be above the graph or below the graph? At this point, at these points on the red curve, which is of quartic function, the concavity is changing. So what happens to the tangent at this point?
Is that, I don't know, but is that like the point of inflection?
It is a point of inflection.
But
So
what happens to the tangent?
Yeah. So when you are moving, let's talk about this particular point here. So when you're moving from the left side, it is concave down. Every tangent will be above, right? So at this portion, the tangents are above, correct?
Yeah.
And as this portion, tangents are below the curve. So in between, they will cross the curve. That is very interesting. So the tangent crosses the curve.
Oh.
Tangent crosses the curve at the point of inflection.
Oh.
It doesn't seem to be like tangent across the curve. Come on.
Yeah. Oh, okay.
Are you getting a picture of this?
Yeah.
So when the concavity changes, so that change is the point of inflection. So change in concavity is the point of inflection. And what we notice about tangents at this point is they cross the curve. So we define in a way a point of inflection is a point on the curve where the tangent crosses the curve. Does it make sense?
Yeah.
That's the unique feature, right?
Yeah.
So let me show you now. Another picture here, just summarizing the whole thing, right? So what I've done this time is we have taken a cubic function. So you see this part is concave down,
Yeah.
tangent is above, right? But this part is concave up, tangent is below. At the point of inflection, I've drawn a tangent, right? And that crosses the curve.
That makes sense. Yeah.
You see that? So it's a very unique point on the graph of a function where the tangent will cross the function. So that is one way of defining point of inflection. So at a point where the concavity changes, the tangent crosses the curve. This point is called point of inflection. Is that okay?
Yeah.
Yeah. It reflects on the change in concavity. Does make sense?
Yeah.
Concavity changes at this particular point. Now, you will notice that at this point, gradient is not zero, right? It's a negative
Yeah.
gradient, highly negative gradient. Is that okay?
Mm-hmm.
We have also seen earlier examples of point of inflection in a curve which is cubic, right? Which is
Mm-hmm.
what you have been always saying. This is the point of inflection, correct?
Yeah.
Now look at these 2 points of inflection. Both are point of inflections, correct? We just saw concavity is changing, and therefore these are points of inflection, correct?
Yeah.
Second, if I draw a tangent line, here also, this x-axis is my tangent line. It crosses the curve. Do you notice?
Yeah.
It crosses the curve. So that is what point of inflection is. Perfect.
Oh, okay.
So in this particular case, I took an example where the function for me is x to the power of 5. And we know that the gradient of this particular function will be 5x4, right?
Mm-hmm.
If I take the derivative, I get 5 times x to the power of 4. So that becomes the gradient. Now this gradient is 0 at x equals to 0, correct?
Mm-hmm.
Horizontal line is the gradient at origin. What you also notice is that this horizontal line crosses the curve, and therefore that point is point of inflection,
Oh, okay.
right? The other way, when you see the graph, you see that the concavity changes. This is concave down, and that portion is concave up.
Hmm.
The point of inflection is where the concavity changes.
Changes. Oh, okay.
So we have two very good examples here where we want to say that point of inflection may occur if the first derivative is 0 and the second derivative is also 0. We'll talk about second derivative slightly later, but we can say that the point of inflection may occur if the first derivative is 0, and point of inflection may also occur if first derivative is not 0, correct?
Mm-hmm.
So that means that we cannot really rely on first derivative test for point of inflection, correct? Because it may be 0, it may not be 0, right? So that is
Oh,
complete stuff, right?
yeah.
But we can definitely say that we should not derive at the result of point of inflection from the first derivative because it makes no sense.
Yeah.
So we'll leave the first derivative only to find maximum and minimum values, not the point
Oh,
of inflection. Is that clear to you?
yeah, that makes sense.
Because it's very important. Many times I've seen students really concluding from the first derivative that at this point we have a maximum, right? We say this point maximum, that point minimum, and the third point is point of inflection. No, you cannot derive from the first derivative. You cannot have a concluding remark saying that that is something. Is that clear to you?
Oh, so it has to be the second derivative if
Yeah,
you want to make a
or something else,
conclusion.
or something else. Or from the graph you can see that the concavity is changing.
Changing. Oh, okay.
Then you can say that. Or you can see from the graph that the tangent is crossing the curve,
Oh,
right?
okay.
But you cannot conclude these things from just the value of point first derivative, correct?
Yeah.
So never relate first derivative to point of inflection. This is very important since in a multiple choice question, I can say that first derivative can help you find the following, and one of them will be point of inflection.
Oh, so you would definitely like just cross that off because you know it
Yeah.
has to be second.
Yes, and so that is absolutely clear now. Is that clear?
Yeah.
So that is what I want to focus. The second point is I have a statement here, which is question number 3. Can you please read question number 3 for me?
Graph of the cubic function will always have a point of inflection. Explain.
Can you explain this?
Uh, well, so what you've said is So any cubic function
Yes.
will always,
Have a point of inflection.
yeah, that's true.
Why?
Because the x-axis will always be crossing the point of inflection.
No, the tangent has to cross.
Yeah, that's.
But x-axis may not be the tangent, right? For example, the cubic function which I've drawn here.
Oh yeah, what happens if it's plus?
So this
Oh,
is a brilliant question, Amy. You should think and answer it later. Similarly, here's another question which is very much related, and that's for students' activity. Can you please read the second question?
yeah. So prove that every cubic function f of x equals ax cubed plus bx squared plus cx plus d will have exactly one point of inflection, and this will occur at x equals minus b over 3a.
Excellent formula. So if you have to find point of inflection for any cubic function, you can always use this particular formula, immediately get a result without doing any calculations. And this formula is not given in any book.
All right.
So take a picture of this.
I
And,
need to answer those two questions.
and you need to answer these two questions, right? So one question
It's
says that the point of
just a quick
inflection,
thing.
yes.
With question 3, is it too short to say it will have a point of inflection because the concavity changes?
That's actually a part of correct answer.
Oh, okay. Maybe we'll have to do some more thinking.
But yes, you have to do more thinking. Now, question number 3 is that there is always a point of inflection, and the student's activity is that point of inflection exists at x equals to minus b over 3a. Do you see how they
Yeah.
are? And I've given you the value also. So when we design our test papers, we actually know point of inflection because it's so easy to calculate, right? Cubic divide this value by 3 times a with a negative sign. You get your point of inflection, correct?
Yeah.
Simple as that. But at the end of the exercise, you'll get a technique of doing it, and I'll share with you some more practice questions to give me the result for the students' activity, right? That is uh, sometimes an assignment for students, okay? Now, we'll go further, understanding our parabola and thereby getting into the concept of second derivative. So what we have learned so far, back to our parabola again, y equals to minus x squared plus 4 is your concave down graph, right?
Mm-hmm.
So on this graph, if I find a derivative of this equation, minus x squared plus 4, derivative is minus 2x, correct?
Mm-hmm.
Now, when is the 0? If I get the 0 at x equals to 0 only, correct? We know x equals to 0 is a turning point. So at this turning point, I know that the derivative is 0. It's a critical point, correct?
Yeah.
Second part. If I do the second derivative of this particular function, which is minus x squared, first derivative is minus 2x, correct?
Yeah.
Again, find the derivative of this particular function, then what do I get? I get minus 2. Minus 2 is negative. Means second derivative which I got is less than 0.
Yeah.
So we can conclude that we get a maximum if first derivative is 0 and second derivative is less than 0.
How do you graph that though?
No, the graph is already there.
How does the graph show that though?
Okay, so let us begin with the function y equals to minus x squared plus 4. Okay, let me do one thing. Let me go back to our previous picture and we'll actually go through this explanation because we jumped into the last part of it, and that is answering why a cubic function should have a point of inflection, correct? Let's try to understand this cubic function slightly more in details, okay?
Okay.
Now, Amy, can you read this contents for me for point of inflection?
Yep. So graph of the function f of x equals x to the power of 5 is shown. It does not have any local maximum or minimum point, even though the gradient of the function f prime x equals 5x to the power of 4 is 0 at x equals 0.
Yes.
At the point 0, 0, the tangent crosses the curve. Yeah. Such point where the tangent to the curve crosses the curve is called the point of inflection.
Right. So you notice that this particular graph does not have any local maximum or minimum,
Yeah.
although it has a stationary point. Stationary point means that the derivative is 0, right?
Mhm.
So at a stationary point, it is not necessary that there will be a local maximum or minimum. In this particular case, what you also notice is that the x-axis crosses at 0, and that is also a tangent because the derivative is 0, right?
Yeah.
And this point is called the point of inflection. So let's read further.
It is important to note that point of inflection may occur when f prime x is not equal to 0. So graph of f of x equals x cubed plus 6x squared has point of inflection at x equals minus 2. The gradient of the tangent is negative, not 0 at this point, as shown in the figure.
Yes. So there is a point of inflection at this point since the concavity changes. And we also notice that the gradient, the tangent line has been drawn, gradient is not 0, right?
Yeah.
Has a slope which is negative. So we can also have point of inflection even though the point is not stationary. Is that clear to you?
Yeah.
Okay.
Oh, okay. All right, okay. At point of inflection, the concavity of the curve changes.
That is primary. At point of inflection, concavity of the curve changes. Second, if you graph a tangent, it will cross the curve. Okay?
Okay. So those are the two main points about
Yes, point of inflection.
point of
Correct.
inflection. Okay. So tangent is above the curve if it is concave down, and the tangent is below the curve when it is concave up. Okay.
Yes.
At the point of inflection, as the concavity changes, the position of the tangent and it crosses the curve.
Yeah, the position of the curve changes. Or you can say at the point of inflection, as the concavity changes, the tangent crosses the curve. Okay?
Oh, okay.
Because it is positioning itself, the sentence is not correctly framed, from above the curve to below the curve. Do you understand?
Yeah.
Just to come from above the curve to below the curve, in between it crosses. That is what I'm
All
trying
right.
to say.
That
But
makes sense.
wordings are slightly different. Okay. So I think now our discussion on point of inflection, we have understood clearly what it is, right?
Yeah.
Now, so let's move on to the next topic, which is finding the derivatives. Okay.
Yeah. Mm-hmm.
We'll come to this later. So now let's try to understand what really the second derivative is, right? So I'll give you the concept behind it. Now we'll again begin with the parabola, which is y equals to x squared minus 4. You can always find the gradient dy dx, which will be 2x, correct? Now
Mm-hmm.
gradient, as you know, is a function. 2x is a function, right? So you can always find gradient of the gradient.
Mm-hmm.
Perfect. So the idea is
Right.
you have a function, you can find gradient of the function. Now you have a gradient, you can find gradient of the gradient, and that is what we call second derivative, because second time you're finding the gradient of the same function.
Oh,
Does it make sense?
okay. Yeah.
Right? So can you now read this from second derivative onwards?
Yeah. So consider the parabola y equals x squared minus 4, which is on the right. Gradient, so the derivative of that function is 2x.
Yes.
Then gradient is a function, so represented by a straight line with the constant slope of 2.
So because it is 2x in this case, so that is your gradient. Is it okay?
Yeah.
Half of the gradient for the parabola.
Now gradient is rate of change. Gradient is rate of change's position on the curve.
Position on the curve. So when we say gradient, it is basically you're looking at each position on the curve. So gradient is rate of change in position on the curve.
Oh, okay.
So you have rise over run, correct? So you take any
Yeah.
points and then you say, what is the change in this, right? Rate of change in this. Rise over run. That is what gradient is. So when you're
Yeah.
talking about gradient, it is change in position, rate of change. Is that clear to you?
Yeah.
Now, change in gradient will be the derivative of gradient itself, correct?
Yeah.
So if I want to analyze the change in gradient rather than change in position,
Oh, yeah.
because gradient is a function, so what we have done is we are finding change in gradient, rate of change of gradient itself. So dy dx is your gradient, correct?
Yeah.
And second derivative is rate of change of gradient.
Mm-hmm.
So the same function which we began with, y equals to x squared minus 4, we found its first derivative. We're calling that to be a gradient. And now again, we are finding rate of change of the first derivative, the gradient, and we get the second derivative.
Yeah.
So in this particular case, the first derivative was 2x. And when you find derivative for the second time, you get the result as 2, which is a constant. So which is positive constant, a straight line, which will be like horizontal. Is that clear to you now?
Yeah.
So rate of change of gradient in this case is confirmed as 2, a
Mm-hmm.
constant, which is the slope of this particular line. Slope means gradient. Do you see that?
Yeah.
Now we kind of related it. But in the whole process, what we also learn is that you can find a gradient and you can find gradient of gradient. And when we do so, we call it second derivative. So second derivative basically is gradient of gradient or derivative of derivative. And we write it as d2y by d2x, right?
Mm-hmm.
d2y over d2x, that is how we will say it. Well, you can now see, we can again find gradient of this gradient, right? So we can have
Yeah.
d2y over d3x, and we can actually continue this process. So in general, we say dny over dnx, where nth derivative, this will be called nth derivative. This is second derivative. So dy dx will be called the first derivative, d2y dx will be called the second derivative, and this will be called nth derivative, n times differentiated. Is it?
Mm.
So for many functions, we can actually continue finding derivatives after derivatives. There may be functions which may give you the same thing repeated over and over again, which you'll learn. For example, you've seen the sine and cosine graph. So if you draw tangents at the sine graph, you actually get a cosine graph. And when you do the gradient of the cosine graph, you get the sine graph. So they kind of flip.
Oh.
And you can continue this process endlessly and keep on finding the derivatives. Okay? So that's very interesting things. Anyway, you got an idea that it is not, the story doesn't finish at just first derivative. We could continue finding derivatives after derivatives and learn more about the function.
Yeah.
Right? Now, the question for you is question number 4, Amy. Can you answer this particular question?
How many times can you differentiate a polynomial of degree n?
Yes.
Well, I would have thought, so whatever the degree n is, you would just do it that many times.
That should be correct. Can you give
Minus
the reason
1.
why?
Oh, because when we have the, wait, so how many times can you differentiate? Okay, so let's say you have something, so let's say we had, let's do a quick simple example. So let's
X squared.
say
Begin
x
with
squared.
X squared. Yes, okay.
So the derivative of that, you don't even have to look what comes after that because the highest power is 2.
Yeah.
So you would just do the derivative of that would be x to the 1, and then derivative of that would just be 2, like
Yeah.
on its own without the x. So you can only do it twice. So that's, if it was cubed, you can only do it 3 times because you will end up with a constant in the end, and then you can't do a derivative of that because it's just
No,
0.
you can do. So you can do
Okay.
derivative of 2, which will be 0. But then after 0, it finishes. Do you understand?
I thought 0 didn't count.
Yeah. So now, if it is x squared, we do the first derivative, get 2x. Then we do the second derivative, get 2. And third derivative we could do, we'll get 0. So we could do n plus
Uh,
1 derivatives for any polynomial.
all right.
N
So
plus
if 0 counts, then n plus 1.
Yes. So
Okay.
that is what it is. Okay. So you could actually, then you get finally zero, and zero after zero is only zeros, nothing left for you to find to get derivative for. Okay. So we have actually understood that you could actually differentiate a function many times. And when you
Yes.
differentiate a function, you do get more information. And here we're going to relate second derivative with the concavity itself. Again, back to our quadratic function, we'll begin with y equals to x squared minus x squared plus 4 or x squared minus 4. So we have two parabolas, one opening down, the other one opening upwards. Now, if
Mhm.
I find the derivative of this function, the first one, I get minus 2x. To find the critical number, I have to equate it to 0. So we find that this 0 happens to be at x equals to 0. Is that clear to you?
Yeah.
We know that it is concave down. However, if we find the second derivative, we get the value minus 2. Minus 2 is less than 0, correct? Minus 2 is less than 0, and we are seeing what we see here is maximum. So we kind of correlate that if the first derivative is 0 and the second derivative is less than 0, in that case, we are looking at maximum. Do you see that part? So we
Yeah.
can look at it and then get to our rule. So we can make a rule that at any point, if the stationary point has been declared at that point, then we just need to find the second derivative and check whether it is positive or negative. If the second derivative is negative, then stationary point represents a maximum.
Oh, that makes
If,
sense.
yeah, if the second derivative is greater than 0, in that case, the stationary point represents a minimum, right? So the simple calculations which have been shown here for this particular parabola has been, is kind of what we are saying is true for that. Is that clear to you?
Yeah.
So, I mean, I've summarized this right here. If you could read this.
Yep. So nature of stationary point can be confirmed with second derivative also. So if the second derivative is negative, then the stationary point is a maximum. If the second derivative is positive, then the stationary point is a minimum.
Correct.
So the conditions for maximum minimum is given with a formula
Well,
there.
that is how it is, right?
Mhm.
Now, here is question number 5 for you, which is describe the nature of graph where the second derivative is 0. Now, for second derivative being 0, we really can't say much at the moment, correct?
Mm,
Because, uh,
just be points
yeah,
on 0.
yeah. So we'll actually learn more how to describe nature of graph when the second derivative is 0. Now, just as we were learning about the first derivative, what we did was we found the critical numbers or the stationary.
Yeah.
So when we found the critical numbers, we said, well, the critical numbers are when the first derivative is 0 or it does not exist. Correct?
Yeah.
Similarly, we are going to now analyze the second derivative. We say, well, to find the critical numbers of second derivative, we have two conditions. One of them is that the second derivative is 0, and the other one is second derivative does not exist.
Mhm.
So because, derivative of a derivative, we are following the similar process. So same things which we did earlier could be replicated, kind of, right?
Yeah.
So in the first derivative analysis, we found the graph being increasing and then decreasing. So we hit a maximum by the analysis of the first derivative. Now in this exercise, we are going to analyze the second derivative to learn more about concavity because we found that second derivative has something to do with concavity. Correct?
Yeah.
Now, let's take an example to check this out. So in this particular case, I have example, which is example number 2 for you. It says point of inflection changes in the second derivative signs. Okay, so example number 2, point of inflection, change in second derivative sign. Okay,
Mhm.
We are given a function which is cube root of x. So this graph is cube root of x. You can clearly see from the graph it is concave up here, correct?
Yeah.
And then concave
Concave
down.
down.
That means we are expecting a point of inflection at 0, correct?
Yeah.
The question is, confirm that the point of inflection is at 0.
Oh.
So how will you confirm this? Okay, so what we can do to confirm this, that at point of inflection, we define what is the point of inflection? It is a point where the concavity changes, correct?
Hmm.
We also learn that if the second derivative is positive, then it is concave up,
Yeah.
parabola. And when the
Yeah.
second derivative is negative, it is concave down, correct?
Yeah.
So we basically want to show that this portion, second derivative should be positive, and in this portion, second derivative should be negative. If we can show that, then we are sure that there is a point of inflection at 0 or the
Oh.
origin. So that is the concept. Is that clear to you?
Yeah.
So we begin by writing the function itself, which is cube root of x. We need to find the derivative of this particular function, y equals to cube root of x. You can write this in the exponent form, find the derivative. So derivative will be 1/3 of x to the power of minus 2 over 3. The critical number at this particular stage, as you know, is the one where the derivative is 0 or it does not exist. So in this case, it is definitely x equals to 0 where it does not exist, right? It is in the denominator. So that's our critical number for the particular function. Correct? Now, let's find the second derivative. When you find the second derivative of this particular function, which is 1 over 3x to the power of minus 2 over 3, you get this result, correct? It gets
Yeah.
multiplied by minus 2 over 3, and you get minus 2 over 9 x to the power of minus 5 over 3. Second derivative actually represents us with concavity, right? It hides the information about the concavity. Now, what is the critical point here? Again, we try to analyze when is the second derivative 0 or when is the second derivative not existing, does not exist, right? So since
Hmm.
x to the power of minus 5 over 3 at x equals to 0, the second derivative does not exist
Wait, how did you figure that one out?
because x is in the denominator, right? If I put x equals to 0 here,
Yeah.
in that case, second derivative will be does not exist, right?
Oh, okay.
Or
Yeah.
minus 5 over 3, right?
Yeah.
It
Yeah.
is the denominator. So that is the only value of x at which we have a critical number, correct? So for second
Oh.
derivative, the critical number is at x equals to 0. So with the help of our interval table, we'll try to analyze the concavity this time. So just make a table, x equals to 0, take a point on the left side, let it be x equals to minus 1. On the right side, x equals to 1. Now in second derivative, put the point minus 1 there, substitute minus 1. If you substitute minus 1, you get positive result, correct?
Yeah.
Minus minus becomes positive. And when you substitute 1 there, you get a negative result. Positive means concave up. So just before x equals to 0, the nature of the graph is concave up. And afterwards, it is concave down. That means
Oh.
at x equals to 0, the concavity changes.
Yeah. That makes sense. Oh, okay.
So that is how
It
you
goes from up to down. Yeah.
up to down. So that is how you explain that the point of inflection exists at the origin.
Hmm.
Now, this is another way of saying that if I am given a function, I don't know about its graph, but I want to know where is point of inflection. What should I do? Can you?
So two main things with point of inflection. It's all about, does the concavity change? That's
Yes,
one question you ask yourself.
yes,
And second one, does the tangent cross the function or the curve?
yes. So
Is that
to find the point of inflection, we have to find the second derivative. Correct?
Yeah.
And in second derivative, find the critical numbers. The critical numbers will be when the second derivative is either 0 or it does not exist. Now, for each critical number, we have to analyze the region before and after, as we did with the help of this table. And
Mm.
notice that at the critical number around it, the concavity changes, then the point of inflection exists, otherwise not.
Yeah.
Perfect. Now,
So just sorry, a quick thing. If
yeah,
it went on two sides of the zero, if it was concave up, then you can't say at
no,
zero it's
it's not.
inflection.
Yeah,
Oh, okay.
we'll have many examples like that also.
Okay.
Where so just by checking the critical numbers, you cannot confirm. You have to do the test using this interval method. Is that okay?
Okay. Yeah.
Important thing here is if my question, as it was in this particular case, confirming the point of inflection, this exercise which I did, does it make sense?
So that's the thing you did with the first derivative.
Oh, there was no need to find critical numbers for the first derivative since we are not going to use that information.
Oh.
So when we're talking about point of inflection, we definitely
Second
need
derivative.
we definitely need what first derivative is so that we can move on to the next step of finding the second derivative. But there is no point in analyzing the first derivative.
So you're saying you don't need to do any of that part?
Not at all.
Oh, okay.
Unless and until we were also interested in finding maximum or minimum or something else. Is that clear?
Yeah.
So
Yeah.
not required. Now, why these things are very important to understand? In a test paper, you do not have a minute to waste. So we have to save all these times and clearly avoid. Is that clear to you?
Yeah.
Move from this step to the second step of finding the second derivative, and boom, you get your answer there, right?
Oh.
So because in test paper, as seen wasting time, test papers are very well balanced, and if you waste time in one question, you tend to lose next.
Oh, okay.
Okay, now note, point of inflection may exist at a point where the second derivative does not exist. Does it make sense to you? It's just shown here, right? Second derivative does not exist. However, the point of inflection exists, correct?
Yeah.
So remember, a critical number is a number where whatever we are trying to analyze could be zero or may not exist.
Oh.
Whether it is a critical number while analyzing the first derivative or the second derivative or thereafter.
Yeah.
Now here is another question for you. This is the last question. Amy, you can make a note of this. Read it for me first, and then talk about it.
Determine any point of inflection for the graph of f of x equals 1 over x squared plus 3.
Perfect. You can add to this question, find local maximum and minimum also.
So that means you have to do the first derivative and second
Also,
derivative.
perfect.
Okay.
Yeah. First derivative analysis, find local maximum minimum also. And then from first derivative, move on to the second derivative and confirm that do we have any point of inflection? If yes, find the point of inflection. And also remember, when we are trying to find the point of inflection, we need to report both x and y values, the coordinate point, right? So in the previous
Yeah.
example, just saying that the concavity changes at x equals to 0 is not really sufficient. I should conclude by saying that the point of inflection exists at the origin, right? However, it was already given in the test, the question itself that it is at origin, and so it was not very much required. But anyway, it is a good practice to write down the point of inflection rather than just the x value. Is that clear?
Yeah.
Okay. So that's where we are going to end today's lecture. Amy, can you summarize for us what did we learn today?
Yeah. So we learned about the point of inflection, and there's two things about it. So number one being the tangent. Oh, sorry. The concavity must change. doesn't matter if it's down to up or up to down, it should change in order for there to be a point of inflection. And number two, on a graph, the tangent should cross the function or the curve. So that's how you get the second derivative. And finding the second derivative, you obviously need to find the first derivative, and then find the derivative of that derivative. So yeah, and that's when you talked about finding the gradient of the gradient, which makes sense. What else?
If the second derivative is positive, then what can you say about the concavity?
If the second derivative is positive, then the concavity is up.
Perfect. That is the right way. Concavity is up. And if the second derivative is negative, then concavity is down. That is kind of important. So if it changes from positive to negative, you know it changes from up to down, right? Or down to up. And there you go. You have a point of inflection, correct? Simple as that.
Yeah.
So that is very important. And I hope now, since you have clear idea about the nature of the graph, whether it is concave up or concave down, you also know how to find maximum and minimum. You
Yeah.
also know how to find the point of inflection. So as an added exercise to question number 4, sketch the graph of 1 over x squared plus 2 or whatever it was, correct?
Yeah.
Graph. That is with exact values. Perfect.
Just a quick thing about sketching graphs.
Yes.
If I have the derivative, let's say in a form like x plus 2 and then bracket x plus 5 cubed or something.
Okay.
Do you just sketch it like as if it was a normal function?
Yes, yes. All as one function. Correct. It's like polynomial. You got so many factors multiplied, but you get one graph with so many zeros and end behavior.
Yeah.
So you have to follow the complete algorithm of sketching a graph, which we discussed earlier. You should know what kind of function you're working with. Now, if you're working with a rational function, it may be a good practice to also look into asymptotes, because all the rational functions may have asymptotes, right? Vertical and horizontal asymptotes. And behavior of the graph, x-intercepts, the y-intercepts, and now we know local maximum, local minimum, and the point of inflection. So once you put all these points together, you will get a good graph.
All right. Okay.
So try to sketch this particular graph, and while you do so, let me know if there's any difficulty. I also share with you some more videos to, help you out in understanding whatever we have learned today. Okay.
Okay.
And from tomorrow, actually, we'll go to curve sketching tomorrow, and we'll look into curve sketching algorithms and understand this process of sketching graph in more details for any function, right?
All right. Okay.
Okay, great.
That makes so much sense. Thank you so much, sir.
Thanks. My pleasure.
Really appreciate it.
Thank you.
Bye, sir.
Bye.